string. So the second character, let me put it this way. The second character of my string is the 100th character of my alphabet. This is the way to put it. Therefore, multiply by 3 to the 100th. Now, this is like genius, right? Now take the third, that's confusing that that's also a 3. Let's change it to 19. Take the third character of my string is the 19th letter from my alphabet, and so I'll raise 5 to the 19th. Wait, your minds don't seem to be blown right now. I know it's Friday and we've been talking for over an hour, but wait, is this kind of like amazing? I'm essentially converting every single, what I'm really doing is I'm converting every single character into a number. Think of it as just like the ASCII code of that character. And now, given the ASCII code of some string, you could think of that as simply like a sequence of numbers, each representing the ASCII code for that character set. And now you're making a gigantic number, which is
so each string is just a natural number.
Each string is just a number. And so let me just do one more, right? This is going to be 7 to the 9th times 11 to the 1 times 13 to the 15th, all the way out to, let's say, like n is, well, let's just stop there. Okay, good. In other words, says Nate, what we have really done is we've created this big function f, which takes you from the set of strings, finite strings, that's really important, the set of finite strings to the naturals. Every single possible string can be coded as a natural number by taking the index of the characters of that string and putting them up into the powers of the primes. Yes?
How do you prove that it's unique?
It's unique because of the fundamental theorem of arithmetic, which says that there's a unique factorization of any number into powers of primes. Sorry, I should probably mention that. I took that as like obvious, but he was in the class where you learned it and he didn't think it was obvious. Yeah, so right, given any natural number, okay, so now suppose I give you some natural number, right? Let the natural number be like the biggest freaking number you ever heard of, like, you know, hundreds of digits, okay? Well, that number can be factored down into a product of prime numbers. And so by getting the product of primes, you can recover then the coefficients, not the coefficients, the powers. And then from these powers, you can consult your alphabet of symbols and you can reconstruct the string. Does everyone see it? Yeah, I'm calling this coding in a real sense, like the coding is reversible. Is everyone following me? I hope you all are. Woo, okay, good. This is in fact, what kind of a function is this? It's probably not a bijection, it's a injection, because many numbers probably won't get, I guess maybe it is a bijection actually. So I suppose every real number can be factored into so yeah, I guess it is a bijection, right? Now it might be like maybe I can't get like 0 or something, you know, or something, some crap like that. Yeah, 1. It's like almost a bijection, but it's definitely an injection. Okay. All right, this should change your entire life. Peter, this means that there are only a countable number of strings, finite strings.
Now I can change the world.
Yeah, because now, what does this mean? What this means is, this is like the joke, did you ever hear the joke, just the second Shakespeare reference today. Did you ever hear the joke that like, an infinite number of monkeys given an infinite number of time will type out all the works of Shakespeare? Has anyone ever heard that joke? That's like a joke. Or just like a fact, right? And the idea behind it is like you get some monkeys and they just like type like basically like random keys on a typewriter, right? And almost everything they type is going to be like garbage. But if you let them type forever, they will die. But instead, you get a robotic monkey. So instead what we do is we enumerate all the strings of English, okay? So first string, A. Second string, probably like B. Second string, AA. Then AAA. Then Okay, so we're going to just produce like many strings of ever and ever. Every conceivable combination is going to come out, right? And so eventually, one of my strings will be like the entirety of Hamlet written in one continuous long string, including like some like new line characters and stuff like that, right? Like, you guys get this? This is like amazing. What this means is there are only a countable number of like possible strings. And that's even assuming that the alphabet is countable. Probably Shakespeare only needs a finite number of symbols, presumably, right? To do his, unless he has, yeah, let's leave it at that. Okay, so, wait, so what's the implications of this? Turn to page 6. Turn to page 6. What this means is if there are only a countable number of strings, but every proof is in fact just a big freaking string. No, Ipsha, I heard that. There are only...
I thought you said this was not the last. I thought you said the other one was the last one.
Oh, that's true. No, we're not actually going to do a fixed... Well, I guess we are. What I intended to do was to... Oh, I really need like... How did I run out of time? Stupid transcendental numbers. God, give me this back for a second. So, what do we need to do Fitch-style proofs? I'm just going to talk this out because I don't have time to write on the board. We need some symbols, right? We need commas, parentheses. We need the connectives. We need the symbols of piano arithmetic. What are the symbols of piano arithmetic? 0, successor, plus, times, etc., right? And then we need some variables. I have created a new special proof character called tab in, tab out, and a new line character. Okay, and now what I want you to do is start filling in this thing with numbers. How much time do we have?
Oh, yeah.
Oh, this is like just a total failure, right?
Yeah, literally.
Do you get it? Do you get the gist of it? I'm going to write this out. What it means is you take every single character that you need to produce a proof, right? You give it a number. Now you write your entire proof out. Okay, if you stick to the Fitch-style proof rules precisely, I mean precisely, then you don't really care, then the reasons are irrelevant, right? Then like the whole program just crashes if it's like wrong. So let's just assume it's right, okay. So then just the parts, just the main bodies, and then also we have this special tab in, tab out character, and a special new line character. Do you agree that the entire Fitch-style proof could be coded in some extremely unforgiving language like Java, such that every character needs to be exactly right, or otherwise it wouldn't compile or whatever, yeah? Okay, so this should blow your mind. Every proof by its nature must be finite. Right? We don't really accept an infinite proof. That's just not a proof at all. So if a proof of a theorem has to be finite, and it is in principle formalizable as a Fitch-style proof from the axioms of piano arithmetic, even though I have a countable number of axioms given that weird thing, that's still okay, then what that means is there are only every proof is really just one long string of characters, and every proof can be coded into a long string of numbers, which can be in turn coded into a single number. There are only a countable number of like possible proofs. Can we prove everything? Are there an uncountable number, perhaps, of truths of arithmetic? Is a question you need to start asking yourself. And somehow, if we can only ever prove a countable number of things, I'm starting to feel like my powers are not quite so infinite as they used to be. Are you with me? The very nature of proofs. All right, good. We'll do the rest of this package somehow. And I'll see you guys, I don't know when. Yeah, I guess I'll probably see you before that because I'll probably have to come back. We have a night period.